Yeah, because honestly, like when you come to the test, how different can I possibly make the questions for a lot of these things? Like scientific notation, you're converting in, you're converting out. Can it look very much different than your quiz? Nope. Counting sig figs, is it going to look very much different from your quiz? Is there any sort of like weird, wacky things I can do? There really isn't at this point. You're making measurements. There will be pictures of things and you'll make a measurement. It's basically like if you took all your quizzes and stapled them together and made them into a reasonable size for one class period, that's what your test is going to look like, except there will also be some stuff on solutions and mixtures. So I have here some milk of magnesia, which you can get at your local drugstore if you want it. Can you guess what one of the components of milk of magnesia is? Magnesium, yes. In fact, there is no milk. However, there's a reason they call it milk of magnesia. Yes? Why do they call it milk of magnesia? Looks like milk. You can drink it. In fact, it is an antacid. This one is flavored like mint, and it contains, what is it flavored with? It says it doesn't contain any sucrose, so that means it doesn't contain any sugar, but I don't know if it's got anything else in it. My eyes are too, like, I've got old eyes. I cannot read this tiny little print anymore, okay? When you turn 50, you will no longer be able to read this tiny little print, so appreciate it now. You'll be using your phone to take pictures of things and blow it up so you can actually see it. Anyway, it's an antacid. And so if you had like heartburn or upset stomach, you could drink some of this stuff, should you want to. And does anyone know something that might act against an acid? Yes. A base, yes. So something that acts against an acid is a base. See if you can remember, and if you can, tell your partner what a base has in its chemical formula.
This was last year, right?
Geo, you're very close. OH. You could write it as you could write it as HO, but it's almost always written as OH. Does anyone know the charge on that? It is negative. And our other ingredient we said is magnesium. Oh, do you know the name of this ion? That anion. It is an anion because it is a negative ion. No, anion is negative. Cation, because, and you can remember that because cats have paws. So, or the T looks like, that's how I always did it. But then I learned that cats have paws. And then I can draw like a little picture of a cat and paws, and it's like so much fun. And I just can't like get over it. So anyway, anions are negative because it sounds like onion. And what do onions make you do? They make you cry, and crying could be a negative thing. If you're like crying because of an onion, that's never positive, right? So anion, which is a negative ion. What is the name of this specific anion? Hydroxide, yes. Okay? Now, if you can see one of the periodic tables, you can help out your classmates who cannot see one of them. Can you find magnesium on there? It is Mg. What column is it in? It's in column 2, which is the alkaline earth metals. That's correct. I don't either. Go talk to our administration. They love it. Anywho, we have magnesium. It's in column 2. It's an alkaline earth metal. And guess what the term alkaline means? I am recording, actually. It's on the other screen because I've sort of run out of space there. What does the word alkaline mean? It actually means basic. So alkaline means basic, and not basic like as in simple, basic as in a base. Because actually, if you take magnesium metal and you throw it into water, it will actually produce magnesium hydroxide. Okay? Now, magnesium is in column 2, so what charge is the magnesium ion? It's positive. How much positive? It's in column 2. Everything in column 2 has a charge of plus 2. What do things in column 1 have a charge of? Column 1 is a charge of plus 1. Column 2 is a charge of plus 2. That's all you need to know for today. We'll do other ones later. Yes? Oh, yes, thank you. So it has, when we have the ion, it has a charge of 2 plus. So if I have the magnesium ion, Mg, and I have the hydroxide ion, OH minus, what would be the, try and write down somewhere, scrap piece of paper, whatever, the correct formula for that compound. Does this make you happy? Does this formula fill you with joy? Or does it irritate you? Why is it irritating? Because there's only 2 hydrogens, there's not 2 oxygens. What am I missing? The brackets. Yes, 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 there we go. No, it's a subscript. Okay, the numbers go at the bottom. Why not a superscript? Because we use the superscript position for the charge. Yes, so if I had nitrate, for example, NO3, it has a -1 charge, so I've got a spot for the number of atoms, and then I have a spot for the charge. Yeah, good question. I like it. All right, so that's what we have in here. What else is in this beaker? Yes, so now that we've had a hiccup, what else is in the beaker along with the magnesium hydroxide? Well, there is air in this part up top, but how about in this part down here? Now, we've talked about ionic compounds, yes, a little bit? A small amount? Have you seen something that looks like this before? Okay, we have alternating positive and negative ions. This whole structure, it's not just a two-dimensional structure. I am just incapable of drawing it in 3D. Ooh, I did it. That is a crystal lattice. That's good, that's good, that's good. Okay, and it has a three-dimensional structure. It is an ionic crystal lattice. Now, there are metallic crystal lattices, there are molecular crystal lattices. But if you just call it a crystal lattice, 99% of the time we're going to be talking about an ionic crystal lattice. Okay? Now, this ionic crystal lattice, what kind of force is in between the positive and negative ion? Yes. BW is between. Are we good with that? Okay. Yes. The force between the positive cation and the negative anion is an ionic bond, and it is strong. Yes? Covalent. Huh? Oh, sorry. Yes. Yes. Between them, intermolecular forces? Yes. Okay, so our ionic bond is strong. And who is our most famous ionic compound that we know of? NaCl is our most famous ionic compound, yes? We all have it in our kitchens. This guy right here is table salt. What state is it at room temperature? Yes. So why is sodium chloride a solid at room temperature? Why are those little ions stuck together in that very organized, rigid formation rather than just flowing all over the place like a liquid? Because they're bonded together, and they're bonded together very strongly. So strong, strong bonds mean you're going to have a solid, because there's strong bonds in between every ion. Now, magnesium hydroxide. What kind of a compound is magnesium hydroxide? It is an ionic compound. So what could you tell me about its state at room temperature? Okay, let's start by telling me about the strength of what type of bond is in it. What type of bond do we have when we have an ionic compound? An ionic bond. And what do you know about the strength of an ionic bond? They are strong. And if it is strong, what can you tell me about its state at room temperature? It is a solid. So what is going on here? Somehow or other, there's a liquid. Oh my gosh, okay. So what else is in this beaker? Along with the magnesium hydroxide. What could possibly make it look like this? Calcium. Calcium would also be a solid. The hydroxide is also a solid. Like the calcium, the magnesium and the hydroxide, when they are together, they are solid. Okay? Water! Yes! I know you had your hand up 17 times. I am sorry, Stuart. You're like, it's water. Come on, just over here, water. Okay, so there is also water in this beaker. Now, is the magnesium hydroxide dissolved in the water? Looks like it. If it was dissolved in the water, it would look like this. Because what does salt water look like? It looks like water, right? So when you have the ions dissolved, okay, so if we had our ions, so here we have NaCl, and it is made up of Na plus ions, and it is made up of Cl minus ions, but it is going to be aqueous. So when it is dissolved, floating around in the water, the sodiums are going to float separately from the chlorides. They're actually no longer bonded to each other. So they go from being bonded to being not bonded. Okay? So in solution, the ions float freely, not bonded to each other. And they are random distribution, okay? They're evenly distributed. And they are invisible. Do you see the ions in here? No, okay? You cannot see the ions in here because the ions are too small for light to bounce off them. Okay? The ions, they're tiny little particles. It's like a single atom. And they're too small for the light to bounce off of. Yes? What makes it salty? It's the sodium ions and the chloride ions that make it taste salty. Yeah. They're still there, but they're separated from one another. And in fact, if they were bonded together, like if you could get your tongue dry enough, like just dry it all off so that, you know, it wouldn't dissolve in your saliva, it wouldn't taste like anything. Because it is actually those dissolved ions that interact with your taste buds, like individual sodium ions. So if you were to taste potassium chloride, it would taste different because potassium ions have a different flavor than sodium ions. And if you ever want to try it out, there's this stuff at the grocery store. It's called salt-free or no salt, and it's got potassium chloride instead of sodium chloride. And you can use it in a salt-reduced diet if that is, you know, an issue, you know, if you have high blood pressure or something like that. Anywho, so they're not bonded to each other and they are evenly distributed, and the ions are too small to scatter light. It's so irritating that my pen is like a half a second behind when I write. But anyway, that's okay. So if we were to shine a flashlight at this thing, I haven't drawn it very well because there's nowhere for it to shine. Let's shine a flash. Let's redraw it over here. Okay, and I'm just going to draw my particles like this. Those are way too big, yes? They would actually, in reality, be so much smaller. And the light from a flashlight, let's say, here's my flashlight. The light goes straight through. The ions are too small for the light to bounce off of. And so what characteristic does a saltwater solution have? You can see right through it. What do we call that? Transparent. It is transparent. Okay? All solutions are transparent. Now, you can have something that's very, very dark. Like if you have Coca-Cola, yes, that's a solution. It contains all sorts of things, one of which is like, a dark colored dye, right? Usually like a caramel or sort of something like that. And it's very brown. But if you spread it into a thin enough layer, you would notice that it is clear, right? It's brown, but it's clear. There's a difference between being brown and cloudy, which is like muddy water, and being brown and clear, which is like Coca-Cola. Yeah? So, this is what we have, salt dissolved in water. Is my magnesium hydroxide dissolved in the water? No, because if it were, what would the light do? It would go through. So what that tells us is that instead of having a solution, MgOH2, we crush it into tiny, tiny solid particles. What do we call it when we have tiny solid particles? We say we have starts with a P, not a weird word, a powder. Yes? Okay. A powder. And what happens is when we have these little magnesium hydroxide particles, maybe we've got like MgOH, OH, Mg, OH, OH, Mg, OH, OH. Even though that looks fairly big, can you imagine if those were all individual particles, it still wouldn't be huge? But, so this is like a particle of MgOH2. It's a small crystal, okay? Doesn't look much like a crystal, but that's okay. And when we put it into a beaker of water, what's going to happen when we shine light at it? Blink, the light gets bounced back, which is why it looks cloudy. I'm going to put large in quotes because they're actually very tiny. But they're large in comparison to ions. So it's bounced off the large solid particles. And in fact, if you want to take a look at it at some point, I have a microscope set up over here. And what I've done is there's a lid on it just because the heat from the lamp will evaporate all the water. I have diluted the milk of magnesia a little bit. Well, in fact, I need to add a little bit more water, but I've diluted it a little bit so you can actually look through it. Hello. Yeah. So anyway, you can look through and you can actually see the solid particles. So what I'll get you to do is I'll get you to go take a look at it along the way. I think by next day I'll bring out some more. I just tried it out today and it looks really good. So I'm like, okay, I gotta look at more microscopes and more stuff. And if you tilt it and then you like focus it, tilt it, put it back, you can actually see the little solid particles like moving in the liquid. Okay, so I'll make sure that if you don't get a chance to see it today, I've got more of these set up next day. Hello. Oh, thank you so much. Okay, so if anybody does have a chance or wants to take a look at it today, I'll just add a little bit more water because, like I said, it's got a light underneath it and it heats it up and it evaporates the water. Okay, where's my water? There we go. Okay. Yeah. Yeah. If you do go and look at it, make sure you take the lid off because otherwise you'll have trouble focusing because there's the lid and there's the thing. Yeah. So if you get a chance today, you can take a look. If not, I'll have it available next day as well. So this is not a solution. Is this a homogeneous mixture or a heterogeneous mixture? It is heterogeneous, even though to the naked eye it looks homogeneous. But, well, you could take two compounds from, yeah, you could still evaporate the water from salt water and get salt and water, right? But what happens is even under a microscope, so let me just make sure I've got this page so it's not like going off in 7 directions. Okay, that looks all right. Okay, there we go. So under a microscope, oh, look at this. Oh, under a microscope, milli, micro, nano, under a microscope, this is what a solution would look like. Whoops. Right? There's nothing. Like, there's water. It's like totally clear. You will see nothing. If you look under a microscope at a suspension, which is what we have here, you'll see like little tiny dots. It's still not like they're not big particles, but they are big enough that under a 4 times magnification you can see them. Okay? Now, why do you think we call this a suspension? Because there are things in it that are suspended. There are little solid particles suspended in the liquid? Okay, and this is a heterogeneous mixture. Whereas even under the microscope, that solution is a homogeneous mixture, because even though it looks like water, there are still ions in there. You just cannot see them. They're way too small to see. Yes, of course. You are going to be making a solution not of magnesium hydroxide, but you're going to be making a solution of calcium hydroxide, because even though I said, okay, this isn't really dissolved, it's little solid particles, a tiny amount is actually dissolved. It's just that most of it is not, okay? So if we were to say, what could we say about NaCl in water? NaCl dissolves in water. What's that word that we use for able to dissolve? Soluble. CaOH2, which you'll be working with, and MgOH2 have low solubility in water. So a small amount dissolves, but not very much. Most of it stays suspended as little solid particles. We're going to do that, so a little bit more will dissolve. Yes. Okay. You can heat it, like you can make things much more soluble than they are by heating them, usually. Now, would you like it for me to print this out? I will do that. Okay, so I'm going to print this out for everybody. We have, what, 5 minutes left or something? Okay, well, 7 minutes. No, we have to do lab safety because next day you're doing a lab. What do you need to wear on your face? Safety goggles. This is a base. Do you want a base in your eyes? That would be very, very bad, yes? What kind of tongs should you use on this beaker? Beaker tongs. You're not going to try beaker tongs for the first time on a beaker full of solution. You're going to try them with an empty beaker because that way you'll have some nice practice, yes? We will be doing things with fire next day. What should you do if you have long hair? Tie it back. What should you do if you catch on fire? Stop, drop, and roll. What should someone else do? Go get the fire blanket, which is right over there. Now, eyes and ears up here. This is like the most important thing of the year, and if you miss it because you're packing up, then I cannot pass you for the course. Okay? So, what happens if you get something in your eyes even though you're wearing protective equipment? You go to the eye wash station. If the eye wash station is way on the other side of the room, which it is for some people, you can start by, don't even worry about taking your thing out of the sink, just get that stuff going in your dilute it first. Eye wash station is over here. All you need to do is push the lever, and it will spray. Okay, there's a lever here, you just push it. What if you get calcium hydroxide on your pants? Now, this actually happened last year. Okay, somebody got it on their clothing, and so up she went onto the counter, put her leg there, and there's like a shower thing. Okay, so she did that. She had to change her clothes, gym strip. Now we do actually have lab coats, so if you're interested in wearing a lab coat, and you're like, I do not want to be putting my leg in the water, you can wear a lab coat. You can also just not spill it, but you know, spills happen.